Hello, students. We're going to talk about equilibrium. This is chapter 13 in your textbook. It is probably the most important chapter in your whole book because it's a foundation for many, many things that you've talked about before and that we'll continue to develop and talk about in this course. This is the idea that when you start a reaction, you have only reactants and it'll start to make products, and then the products will come back in a forward reaction to make reactants. And ultimately, there's going to be a special point where the rate going forward, the speed going forward equals the speed going backwards in the reaction. So that's this important part right here, which is the definition of equilibrium, which is the rate forward equals the rate reverse. And that particular concept is kind of interesting because at that point, there's still motion in a reaction. It's not like the reaction stops. It's just that the relative amounts of concentration of products in reactants no longer changes. And we're going to be exploring that in a lot more detail here in a few minutes. So there's motion back and forth. It's just the rates equal. So let's say you're doing a reaction in a test tube or beaker. It doesn't appear that the reaction is anything's happening with it when it reaches equilibrium. It looks like it's over, but yet there's this steady flow back and forth. And that's where the term dynamic comes in. Anytime that equilibrium state is discussed, is that there's motion back and forth. Okay, this is a reaction of N2O4 and 2NO2. And this is the idea that we start with N2O4 and it's going to proceed forward. So as we look in the graphic here, start off with N2O4, colorless gas, so it's the white ones. Then it starts to make product, NO2, which is a brown gas. And ultimately, over time, right, you get more and more NO2 until equilibrium is reached. And that would be this third one here. This is the equilibrium state. Now, if you notice, there's still motion back and forth, but the relative amounts are the same. So I can count them up: 1, 2, 3, 4, 5 NO2, 1, 2, 3, 4, 5 NO2. It's not the same ones. They've reacted going back and forth. It's just the relative amount stays the same. So the concentration of NO2 and N2O4 is the same at equilibrium, not necessarily to each other, but the relative amounts of reactants and products. So I won't count the white ones for you there, but I just want you to be aware that there's motion here. Okay, so let's tie this into our last chapter. I mentioned the word speed or rate of reaction, that the rate forward equals the rate reverse. And so we can apply some of our discussions from that chapter, our previous one. N2O4 to NO2NO2, I'm going to put the double arrow to show an equilibrium back and forth. And so we can describe the equilibrium the rate law for K forward times N2O4 concentration. And since we said that that equals the rate of the reverse, so if I'm looking at the reverse, K reverse NO2 squared. So this is a lot like the mechanisms that we started to talk about in the fast reactions that were reversible. And what's going to happen here is we can put the K's all on one side. So divide both sides by K reverse. And what we'll end up with is this expression here. But these K's can be combined into big K. And that is what's called the equilibrium constant. This is always the ratio of product over reactant. And in a moment, we'll talk about how we can write what are the rules for writing this expression. So we'll get to that in just a second. Now, this particular K is expressed in terms of concentration. So we call it Kc for concentration. There's going to be all sorts of Ks that we're going to encounter. We're going to encounter Kp for pressure, Ka for acid, Kb for base. So this one here would be Kc because it's expressed in concentrations. Okay, and you don't necessarily need to write, I know there's this EQ here. As we keep going, we won't be writing that in. This is a numerical value to tell us what is happening at equilibrium. Is it product favored or is it reactant favored? And so one of the things that I will be pointing out as we go is kind of this idea of why K is important. Okay, not just mathematically, but conceptually. And here is that understanding. So K tells us what is the extent of the reaction, how strong a reaction is, forward or reverse. So let me put a generic thing here, just A to B. So I'm going to put K equals the concentration of B over the concentration of A. Okay, so if you have a small value for K, that means that the reaction actually, let me do this, a small value for K will mean that you have a lot more A compared to B at equilibrium, that the reaction goes forward, but then it really pulls back towards reactants. So mathematically, then that's going to make K, in fact, I think I'll do this. We'll make that forward arrow a little bit smaller. Oops, I didn't mean to do that. It'll make that forward arrow a little bit smaller. So there's a pull towards reactants. And this is when we say that the equilibrium lies to the left, where the reaction favors reactants. Okay, now what kinds of things would have Ks like this? We're going to be talking a lot about, let's say, weak acids and soluble salts. So we will have all sorts of examples as we keep progressing in our chapters. Now, the other thing is, I'll write it here then, that K in this example is much less than 1 because it's small, right? And so this is an example of where the equilibrium lies left. Now you could have a process. I guess I'll use a different color. Where you have A go to B, but the reverse reaction is not very strong. Okay, in this example, you're going to have a lot of B compared to A, so K is very large. This is a reaction that favors products. In this example, the equilibrium lies to the right. These are reactions that you're very used to doing in lab. So things like combustions, precipitations. These are very common reactions that love to go forward. In some cases, the reverse reaction is so minimal that it's a theoretical discussion. So for us, we're going to be talking a lot about strong acids, for example, in this category. Okay. All right, so let's take a look. I really, really like this slide. Usually I'm not big into the picture ones, but I think this is such a good one. This is showing an example of different reactions. So the first one, the reactant is in blue and the product is in red. So here's our reactant and our product. And what you'll notice is that this is saying that the reaction proceeds, but let's take a look. K is very, very, that's not very, very, it's small, less than 1, correct? You could count them. It's just one product out of 49. Okay. Now, what this is telling us then is that the equilibrium lies to the left. Not super dramatically. Later, when we actually start looking at reactions where the equilibrium lies super left, there's very, very small. And in fact, this guy here is fairly moderate. I'll talk more about that in just a moment. Okay, let's go to the next one here. This one, you have the reactant, and I guess you'd say orange, and product in the light teal green. And so in that case, the reactant forms product, the product comes back. But if you notice, you have a lot more product than you do reactant. So in this case, the equilibrium lies to the right. Okay, now there was this other scenario, and let me write in our K's here. So K would be, again, concentration of product over concentration of reactant. Okay, now this third scenario is one where the reaction goes forward, goes back, and if you notice, when equilibrium hits, you have an equal amount of each. This is really an equilibrium that it doesn't favor right or left. It's a moderate reaction. And it's really our equilibrium point, almost like a true equilibrium, that where the reaction's very reversible. So I actually like those words better. And I messed up on my R there, so let me go back. This is a reversible reaction. And this is really where we begin our discussion in chapter 13. Chapter 13's real focus is this reversible reaction. And it's something we're going to explore, you will explore in your lab class as well. Okay, now if you notice there, the K value is 1. Okay, now I do want to say one thing here, and this slide is a little misleading because they didn't want to draw such a big graphic with the number of spheres they were showing. But the reality is that if we look at our K values, this reversible range is really like 10 to the minus 3 to 10 to the positive 3. And then KCs that are very large, these would be equilibrium lies right. I'll put them here. To give you one example, later we're going to do the chapter on batteries. So like Duracell batteries, talk about how they're used for energy. You're looking at gigantic K values, like 10 to the 54. You see how much bigger that is than these reversible range ones? And then on the other extreme, you could have some Kc values that are tiny, 10 to the negative 18. And so here, it's a spectrum. Okay, but chapter 13, where we begin our journey on this, is dealing with and discussing and understanding this reversible range one. That's where all the problems in the book focus on reversible reactions in chapter 13. Okay. Then, as we keep moving away from this chapter and we start talking about other things, we tend to go then into discussions where the equilibrium lies to the right or to the left. Okay. All right. So there's what's called, I introduced K to you, and there's another discussion on something called Q. Q is the reaction quotient, and the reaction quotient for a balanced equation is given by the following relationship. QC will be the concentration of products over reactants, but we do take into account their exponents by looking at their coefficients. And we'll practice writing these. These are pretty easy for students. Okay, now, what's the difference between Q and K? Okay, at equilibrium, Q equals K. But Q is going to be more generic. It's going to say, hey, you have a reaction. Are you at equilibrium or not? What's the ratio of products over reactants? And if Q equals K, then you know that you are at equilibrium. If it doesn't equal K, then you know the reaction still has to proceed towards equilibrium. Okay, so I think there's an example next. Let's take a look. Okay, it's a picture. Okay, so at some point in a reaction, so this was for the N2O4 going to the 2NO2, that there comes a point over time where Q equals K, and then that's where you have a certain ratio of product over reactant. But as when you start a reaction, you're not there, right? So anywhere along the way to get anywhere along the time frame that you're approaching equilibrium, Q is some other value. So I kind of think of the fact with Q is it's sort of like a snapshot of where you are at in a reaction. Okay, and which way you have to go to get to equilibrium. Oh, click too much. Okay, so we're going to talk more about that concept in a second. The first thing we're going to do, though, is just learn how to write the K expressions. So here's a reaction that involves calcium carbonate to form calcium oxide and CO2. So initially, if we say, okay, I'm going to write Kc for this, initially I might write concentration of CaO times concentration of CO2 over CaCO3. Now that might be where we start. But if you think about the term concentration, okay, that should sound a little weird when it comes to a solid, right? You've never used that term when you're talking about a solid. So a solid will have the same concentration, in other words, moles per liter. And so that particular idea of concentration is, since it's like a constant, actually gets absorbed into the K expression. And so the result of that is the Kc for this reaction up here is concentration of CO2 only. So the bottom line is we do not show, or do not include solids or pure liquids or liquids that are pure in the Kc or Q expression. So this was showing it as Q. And again, Q is the concentration of CO2, but we're not sure if it's at that equilibrium point or not. Okay. All right. So this is kind of a really nice graphic where it's showing the calcium carbonate and CO2 and CaO. And what it's trying to get you to think about is how large the number of moles of the solid are compared to that dilute gas, and how we can think of those as essentially being a constant in this process. So when we're looking then at Q here, or K, depending on if we're at equilibrium or not, then those will just equal the CO2 concentration. Okay, so take a minute, you can pause me, and go ahead and write the Q, the reaction quotient, for each of the following. You do need to balance these equations first. Okay, once you balance them, go ahead and remember, no solids or liquids. What will be included are gases, because they're dilute, and aqueous. Remember also that you do have to balance them, so the coefficients will be the exponents for those. Okay, so pause me and do those. Okay, so here should be the answers. So there's the first one, balanced. And then QC would equal NO2 to the fourth power times oxygen divided by N2O5 squared. Okay, and those are gas phase. Okay, so they're all included there. Second reaction, sodium solid plus water liquid. Well, those are out. We do not include those. So if you notice, the QC is just sodium hydroxide, which is aqueous, squared times hydrogen. And then for the last one, balanced, everybody's going to show, because they're all gases. CO2 cubed, water to the fourth, C3H8, and oxygen to the fifth power. Okay. All right. This part I'm going to do really quickly. I don't want to dwell on it too much, because it's important, but it's not really the most important part of our chapter by any means. So all this is going to say is how will Q or K change if we change the balanced equation? That's all it's going to tell you. So for example, let me go back. Let's say that we have a balanced equation. Let's say Q equals the concentration, let's say A to B. Or K equals the concentration of B over A. Okay, so if for this reaction as written, so let's say K, let's give it a value. Let's say that this value is 10 to keep things simple. What would the K be if I wrote the reaction of B going to A? In other words, the reverse. Well, if you notice, that would mean that my K would be A over B. And do you see how it's the reciprocal of this? This would be flipped. So that would be 1 over 10. Okay, bottom line, if we know the K or Q going one way, we can find the reverse way by just taking its reciprocal. If we have an equation where the balanced equation is multiplied by a factor, so let's take our simple one again. A to B, we'll say KC equals 10. All right, now let's just say that the coefficients were doubled. You know, here's a 2 and 2, right? Same reaction so that we can't change the ratio. What would KC be if I did that? Well, if you think about it, it would look like this, right? KC B squared over A squared, which then would mean that to change it, it would actually be 10 squared or 100. So that's what this is saying. In just a fancier term, that if you change the coefficient, then you would change K or Q, but by that exponentially. Okay, so this looks really scary, but this is just a summary chart. Your book didn't have such a nice summary chart as this, but so I thought I would share it with you. I don't want you to just focus too much on this. This is just more like FYI of how we manipulate Q and Ks. Okay, so I'm going to click. I do want to focus a lot on one thing in this slide. That let's go back to the one that we did earlier. Okay, do you remember where we wrote the K for this, KC, and we said, oh, okay, that just equals carbon dioxide because those solids, the idea of their concentration, there's so many moles per liter that it's like a constant value and it gets absorbed into the equilibrium constant. Now let's think about something. If Kc equals the concentration of CO2, well, that's a gas, and wouldn't it make more sense to talk about its amount as a pressure discussion, right? If it's in a container. If you recall that really pretty picture, the graphic that showed the CO2 buzzing around the mound of the other two solids, calcium carbonate. You can go back. You can go back and take a look at that. But wouldn't it make more sense to describe the CO2 in here with the pressure within a container? And so there is such a thing as expressing K in terms of pressure. So I can write this guy as what's called Kp. Okay, I'm going to put this in really, really big red letters over here. Kp is as important as Kc. And so we can solve equilibrium problems that we're going to have in the next video lecture in pressure. There is a push on the student's part when they see equilibrium discussions in pressure to try and change it to concentration. And that is something you want to resist. You want to get comfortable working and understanding K in pressures. And I'm not sure exactly why, but students sometimes just don't like it as much and they want to go back to molarity. I guess maybe because we're comfortable with molarity. Okay, but we can work equilibrium problems with KP. They make sense. KP makes sense with gases, right? Not with solutions in this. Okay, now here's the other part where, remember from Chem 200 that pressure is related to concentration. And this is going to be a side note. Do you recall which famous equation relates pressure to concentration? What's the most famous equation for gases? PV equals nRT, right? If you notice, I'm probably going to switch out this just to make it a little more dramatic. You see N over V? That is moles per liter, which is concentration. Oh, I didn't mean to do that. I think what it is sometimes when I get talking a little bit more freely, that then I don't focus as much on my pen. So it's fine if you just bear with me on that stuff. Okay, so here, concentration, right? So here's the deal, and I like this easy one here to discuss this, is that we can make a substitution. Like I could substitute for pressure N over V times RT. So let me do that. See that? That's just a substitution for pressure. And then Kp would equal, well, essentially concentration of CO2 times RT. So here's the bottom line with this, is that there is a relationship between Kp and Kc. And that relationship is built around a factor of RT. So you see here, Kp will equal Kc times RT. Now, the relationship, though, depends a lot on what's going on in the balanced equation. So there is one more thing here, which is delta N of gas. So basically the idea is this, that what factor RT is it related to or changing depends on how many moles of gas there are on one side compared to the other. Okay, so let's look at this simple one up here first with the calcium carbonate one. I'll switch colors. I have 1 mole of gas on the product side and 0 moles of gas on the reactant side. And so my change in the number of moles of gas for this is 1 minus 0. So this factor of RT down here is to the first power. Okay, now let's say that the reaction wasn't so simple. Let me erase this. Oh man, that's funny, sorry. Okay, so let's say it wasn't so simple. Let's see what we get. So let's go back to the pen. Let's say it's this reaction 2NO plus O2 to make 2NO2. I have 2 moles of gas on the product side, and I have a total of 3 moles of gas on the reactant side. So what does my delta N for this one? Delta N is 2 minus 3. So Kp will equal Kc RT to the negative 1. So in other words, Kp and Kc are always related by a factor of RT, but it really depends on the equation by how much of, whether how much the Kp is changing from Kc has this RT correction factor, but it depends on how many moles of gas are on each side of the reaction. Okay, there is one more thing here, and I'll erase this bottom part. That there are certain reactions. Let me give you an example. So take a minute for this guy. Figure out what your change in moles of gas are. Well, it's 2 moles of HI on the product side and 2 moles total on the reactant. So your change in moles is 0. So what does this ultimately mean is that for this example, then Kp equals Kc RT to the 0. Well, that's just 1, right? So where you have no change in the moles of gas, Kp equals Kc. Now, all this is really good info, but I want you to really tell yourself one thing, though, as we start to work problems. You do not have to switch Kps to Kcs all the time. As we learn how to do equilibrium problems later, we're just fine working problems in pressure. This slide is just trying to get you to understand that Kp and Kc are related through a factor of RT. Okay, so I'll talk more about that with you as we keep going, because we're going to start to work problems in the next video lecture. Okay, you can do a quick question here, converting between Kc and Kp. So we can solve it real quick. So Kp equals Kc times RT, change in moles. So our delta N for this is 2 moles of gas on the product. There is no gas on the reactant, so that's 2 minus 0. So Kp equals Kc times RT to the second. And so if Kp is given, the RT here, the R is from PV equals nRT. So that's the R that you like maybe better than the one we've been working. Just your regular R. And then this temperature was at 218 Celsius. You would need to convert that to Kelvin. So let's see what that is in Kelvin. That's a really high temp. 491. And then we'd solve for K. And I think the answer is on the next page. So get your answer and then we'll check it. Hold up. I don't know why it showed it as something kind of strange on our answer. Oh, okay. No, we're okay. So we have Kp equals Kc times RT, change in moles, and therefore when we plug in, we should have gotten this answer. Now, if you notice here, this is very confusing because it has the negative there. That's just from the algebraic rearrangement. So kind of, I would say, ignore that for a second. Do it how we were doing it on the previous page where we were solving for Kc. So Kc will equal Kp over RT, change in moles. So if you just stick with that, it's showing it as a negative because it's writing it. You see how that's the same? Those are the same. I find that kind of confusing for you guys. Okay. Okay. I'm going to talk about this slide in just a second. So let me click. Let's do an example. And I'm going to get to the example problem here in a second. Okay, this is the one that I want to do. Here's a reaction, same one, N2O4 to 2NO2 gas. Kc is 0.21 at 100 degrees. Okay, so let's talk about that. We're going to say Kc Oh, we're not going to talk about that. Hold up. It's being very volatile. Okay, so Kc is 0.21. So let's go ahead and write the Kc again. NO2 concentration squared over concentration of N2O4. Okay, and this equals 0.21. Okay, at a certain point during the reaction, N2O4 concentration is 0.12 and NO2 is 0.55. And so the question is, are we at equilibrium? And if we're not, which way is it going to shift to get to equilibrium? Okay, so the way we want to do this is to rely on Q. And just essentially, we have this snapshot of what's going on in the reaction. We're just going to plug in. And let's see where we're at, because if Q equals K, then we know we're at equilibrium. But if we're not, then where are we in the reaction process? Okay, so I'm going to take that squared and I'm going to divide by 0.55 and I get oh boy, I can't even see. So I think I get 0.026, but that I'm not sure on. Hold up. Oh, it's because I have them flipped. This feels more like regular class. I try not to make any mistakes on your video lecture, and you would have been saying, wait a minute, you messed up. So, okay, so let me try that again. We have NO2, so that's the 0.55 would be squared. And I do miss class where we can interact and you can tell me when I mess up. Okay, there we go. I knew that because that was not right. Yeah, I said 2.5 and I'm like, why isn't that coming up on my calculator? Okay. All right, so we just want to know, are we at equilibrium or not? So we're going to plug in to the K expression or Q expression. Okay, now probably if we were in real class, somebody would ask me a question, which is what happened to those molarities? And one of the things that I should have mentioned probably earlier is that officially Q and K have units, but they really are dropped off. So it's the only time in your whole book where we don't worry about the units because we're looking at it as a ratio. Okay. All right. So I'm looking at Q, and if you notice, it's really, really heavy on products, right? Because Q is so much bigger than KC. So it's really heavy on products. You can try to show that with a different colored. Very large on the top part here, right? That's making this number bigger. So if you think about it, if we're heavy on product side, well, that means that it's really going to have to shift back to reach equilibrium. And so we would expect that this would have to shift to the left. Okay? So if you are more of a picture person, we can go back to the previous slide. I didn't like that particular sample problem. You can go through and do it if you want. I just don't like the negative exponents. Okay, let's take a look at this picture. In our example that I just did, our Q is 2.5 and our Kc was 0.21. So in other words, Q is too big compared to K. That means that we're heavy on product and it's going to shift to the left to get to equilibrium, where now 0.21 would equal 0.21, meaning that you're at that point where Q equals K. So I do really like this graphic because it tries to give you a visual of that shifting to the left. Now, I know we didn't do a problem like this, but let's pretend that we did and that we ended up in a scenario where the Q ended up being, I don't know, 0.11 compared to 0.21. Same reaction. You see how that means that you don't have enough product, right? And that's going to shift to the right to try to get them Q to be equal to K. So this is the whole thing about Q, is that Q is just a spot in the reaction as it's shifting right, shifting right, shifting left, and then it's trying to get to that equilibrium spot. And so I really like this graphic to try to visualize it. If you're more of a, you like sentences and reading, then we'll go back to one more slide. And this is a summary slide. This is saying that if Q is greater than K, like we just did in our example problem, then it's too heavy on product and it's going to have to shift back to reactants to get to equilibrium. If we have a scenario where Q is too small, then it's going to want to shift to the right to get to products. And so that's a different snapshot of our reaction. And then ultimately Q will equal K. And at that point, you're at equilibrium and that's it. The reaction has reached equilibrium. Okay, and this is really the importance of Q. So this is something that is very important discussion. Okay, and which way the reaction has to go to get to reach that equilibrium condition. The other thing too to consider, it's something you're going to explore in lab, is that the interesting part about reversible reactions and this moderate range K values that we see in chapter 13 is that these are reactions that like to go backwards and forwards. And so you can literally start a reaction with products and then it shifts left to reach equilibrium. So that's kind of weird. And for us, because all the reactions that we've done previous to this are the ones that like to go forwards only. Okay, so you have to kind of adapt your thinking because this is a new type of reaction for you guys. Okay, it means that in this moderate range reversible reaction that you can shift right to reach equilibrium, or if you had products, you could shift left to reach equilibrium. And then you get to this point where Q equals K. Okay, so you can do that other one. I just didn't like the numbers it chose for it for our first example. The 2.5 and the 0.21 are just a lot easier to deal with.